in the last video for this lecture. What I want to do is first say a little more about the properties of integrals we talked about last time, and then we'll do an example where we compute a definite integral taking advantage of some of these properties. Okay, so first what I want to do is just give a quick review of the properties we talked about and see how some of those properties are examples of others. So here we go, properties of integrals. 2 videos ago, we saw that the definite integral of a constant function, c, from a to b, is that constant c times b minus a. Because what does this integral represent? It's the area of a rectangle with side lengths c and b minus a when c is positive, and it's the signed area of a rectangle below the x-axis with side lengths negative c and b minus a when c is negative. Okay, so we saw last time that the integral from a to b of c times f of x dx, that we can factor out this constant c, and what we get is c times the integral from a to b of f of x dx. So if you think about this definite integral as a sum of rectangle areas, the difference when you multiply this function by c is all the rectangle heights go up by a factor of c. So I just want to point out that this integral of a constant function, property 1, is an example of property 2 in the special case where f of x equals 1. What we get is the integral from a to b of c dx is equal to c times the integral from a to b of the constant function 1. So we just need to know that the integral of a to b of 1 times dx is equal to b minus a. And that's an example of this. Okay, so the first property that we talked about in the last video was that the integral of a sum is equal to the sum of the integrals. And later in the video, we said if you take the integral of the difference of two functions, here I'm calling them f and h, integral of f of x minus h of x, that's the integral of f of x minus the integral of h of x. So I just want to point out that this property 4 is an example of property 3, where we let h of x be equal to the function negative g of x. So again, these two properties are pretty much the same if you let the second function be equal to the negative of the second function in the other. Okay, here's another one that I didn't do in the video last time, but I want to mention. The integral from a to b of f of x dx is equal to the negative of the integral from b to a of f of x dx. That if you switch whether x is starting at a and ending at b versus starting at b and ending at a, all you get is the negative of the definite integral you had before. The reason is that the rectangle heights, which are given by these points, but your function f evaluated at these points, xi, these f of xi's are all the same. But the difference is that in the first case, you have this old delta x, which is b minus a over n, when you have n rectangles. Let me write that a little more clearly, b minus a over n. And when you switch a and b minus a over n turns into a minus b over n. And the only difference is that you're taking the numerator and multiplying by -1. So all of the rectangle areas you get, now you'll have a factor of -1 that switches the sign. At the end of the video last time, we talked about the integral from a to a of f of x dx. That is, x starts at a and ends at a. So when you think of this in terms of rectangle areas, there's just that one value of x. So any rectangle you take, the base is too skinny to actually have any area. So the integral from a to a of f of x dx is 0, no matter what function f of x you pick. So I just want to point out that this function, this property 6, follows directly from property 5. If you let b equal a in property 5, what you see is that the integral from a to a of f of x dx is equal to the negative of the integral from a to a of f of x dx. And if you have a real number that is equal to its own negative, it has to be 0. So that's the review of these integral properties that I wanted to do. And now what I want to do in the rest of this video is one example. Okay, so let me erase in the top here. All right, so let's compute the integral from 5 to 7 of the function 4x plus 3 dx. And first, property 3 tells us that this integral of the sum of two functions is the sum of their integrals. So this is the same as the integral from 5 to 7 of 4x dx plus the integral from 5 to 7 of 3 dx. Okay, well, we know this second piece by this property 1 that I erased. The integral of a constant function is that constant times b minus a. So we know, so by this property 1 that we talked about, that the integral from 5 to 7 of 3 dx equals 3 times 7 minus 5, which is 3 times 2, which is 6. So all we have to do is figure out the integral from 5 to 7 of 4x dx. And we know by property 2 that we can factor out that 4. We know the integral from 5 to 7 of 4x dx is equal to 4 times the integral from 5 to 7 of x dx. So in order to compute this integral, we've now simplified things down to understanding one piece. And that is, what is the definite integral from 5 to 7 of x dx? So what is the integral from 5 to 7 of x dx? And there are two different ways that we could think about this. I'll come back to the second one at the very end of the video. But one thing we could do is just use the definition of this integral as an area, which we're going to approximate using a limit of sums of rectangle areas. So here, we'll let f of x equal x. We'll say delta x equals 7 minus 5 over n, which is 2 over n. x0 equals 5, and xi equals 5 plus I times delta x, which is 2 over n. So where does that leave us? We have to make a choice now about whether we're going to have our rectangle heights be given by f evaluated at the right endpoint of each interval, or by f evaluated at the left endpoint of each interval. So as I said in a previous video, I'm a right endpoint person. So we get a sum from I equals 1 to n of f of xi times delta x, which we can rewrite as a sum from I equals 1 to n of f of 5 plus 2i over n times 2 over n. And now we know that f of x equals x. So this is a sum I1 up to n of 5 plus 2i over n times 2 over n, which you're taking a sum of the product of some things, and you can just expand out that product if you like. So the first term now is 10 over n. And the second term is 4i over n squared. Okay, now we can use some algebraic properties here, like if you have a sum from I equals 1 to n of the sum of two functions, f of x plus g of x, that's the same as the sum of the first piece plus the sum of the second piece. So this is a sum from I equals 1 to n of 10 over n plus a sum from I equals 1 to n of 4i over n squared. This first piece, we know. I mean, you can factor out a 10 over n. And now you just have the sum from I equals 1 to n of, there's no I in here anywhere. So you factor out 10 over n, and you're just getting 1 plus 1 plus 1 plus 1 n times. In the second case, there's an I in the numerator, but every term gets multiplied by 4 over n squared. So we can factor that out. And we get a sum from I equals 1 to n of I. So altogether, this is 10 over n times n, which is 10, plus 4 over n squared times this expression, which has come up a few times already, that we've seen is equal to n times n plus 1 divided by 2. There's a factor of 2 in the denominator that cancels with the 4 up here. There's an n squared in the denominator that you can cancel with this n up here, which just leaves one n in the denominator. So yeah, let me go back up to here. Let me erase. Yeah, what do I want to erase? So Rn now is just equal to 10 plus 2n plus 1, right? This n cancels. You get a 2 here, over n. So that's our expression for Rn. And this area, this integral from 5 to 7 of x dx is the limit as n goes to infinity of 10 plus 2n plus 1 over n. As n goes to infinity, the numerator and denominator are going to infinity, but they do it in such a way that it's not so bad to see what the limit is. This is the kind of thing that you probably learned in Math 2a, that this limit, this part 10, is just 10, doesn't depend on n at all, plus the limit as n goes to infinity of 2n plus 1 over n, which you can think of as 2n plus 2 over n without the parentheses, and that's just 2. So this is equal to 12. Okay, so where does that leave us? We see that the integral from 5 to 7 of 4x plus 3 dx is equal to the sum of these two integrals. The second one is 6, and the first one is 4 times what we just got. So we should get 4 times 12 plus 6, 48 plus 6, which is 54. Okay, so that's one way to do this problem, but we can also use the fact that we know that this integral means something, that it's the area under the graph of some function between x equals 5 and x equals 7. So let's graph that function and see what we get. So here's my graph. Let's say 5, 6, 7, 4x plus 3. When x is 5, this is 23. When x is 6, this is 27. And when x is 7, this is 31. This is a line of slope 4. So here's 31, 23, 27, 23, So what is this figure? It's a triangle on top of a rectangle. And this rectangle has height 23 and base 2. This picture is very terrible. So the area here is 23 times 2 is 46. And this triangle has base 2 and height 23 to 31, 8. So the area here is 2 times 8 divided by 2 is 8. So we can see in a totally different way that the area equals 8 plus 46, which is equal to 54. So we can use two different strategies to compute this definite integral. And if you do everything right, the answers you get should be equal to each other. And that's it.